Alex Cole with BobCAD-CAM here. So in this video, what I would like to talk about is some of the different multi-axis toolpaths, the different strategies, the different operation types that we have, and just a general overview of what they are and what you would use some of these options for. When you're first getting into multi-axis, it can be very intimidating trying to figure out what all these options are. So that's what I want to get into today in this video, is see exactly what all of these operations are. So I've got a couple different part files open here, and what I want to do is just kind of take a look at the multi-axis feature and what toolpath operation types we have to choose from. So when you create a multi-axis feature on the toolpath type page, you can select between wireframe, we have multi-axis roughing and swarf machining, and then we have the surface-based paths. And under the surface-based paths, once that is selected, then you have all these other options for the different types of toolpaths. Now, we've gone through and created images to give you an idea of what each of these toolpaths would be used for. So as we click on each of these, you can see our image updates, and it gives you kind of an idea. But sometimes that can be limiting because these toolpaths all have different options, and some things are better than others for different types of parts. So let's just talk in general about what these toolpaths are. We're not going to get into really deep details or anything, but let's just take a look at them. So the wireframe toolpath works really well for when you want to trim things out using the end mill, so or your cutter. So if I look at a wireframe toolpath, right, we have a simple part here. This is a part that I used for my wireframe trimming video. And so if you are somebody who you need to cut through a piece of material and using the side of the tool, go around and cut that part out. So think of a thermoformed part, a plastic part, a stamped metal part where you're trimming flashing off. It might be with a end mill, it might be with a laser, plasma, or water jet machine. Could be a router. This toolpath is designed for doing just that. So the next toolpath that we have is the multi-axis rough toolpath. So this toolpath is designed for roughing out material in a 5-axis method. And this toolpath takes a bit of calculation time, and it does a really good job of roughing material out while rotating the part. So let's take a look at a couple different multi-axis roughing parts. So here is a multi-axis roughing part. We can see that the floor of this part is curved, as well as the top surface, and then the part is it needs roughed out all in between. So this path is similar to our advanced rough toolpath, only this one is for 5-axis motion. I personally am a believer that in a lot of scenarios you're actually able to remove material faster from a piece by doing 3+2 machining, where you would index to a position, and then from that position do a 3-axis toolpath to remove material, index to a new position, and continue until you've roughed out the part. But sometimes, especially for aerospace parts, you want to do uniform material removal, and this path would be used for that. It can also be used on auger type shapes or screw type shapes, as seen in this part here. Okay, so the next toolpath that we have is swarf machining. So swarf machining is designed to be cutting with the side of the tool, and you can set it up to do step downs and step overs. So if you're roughing material out But think of it like a profile toolpath, but for 5-axis. So that same trimming part that we took a look at, which was, I believe, this part here. So this same part is a really good example of what a swarf path would be used for, where you're cutting around the perimeter or the periphery of a part, and you're going to be cutting with the side of the tool. Now, it's not the only way to cut with the side of the tool. The wireframe toolpath will do that. The swarf machining toolpath will do that. And you can even use some of the surface-based paths to generate a cut with the side of the tool, as we'll see in a moment. All right, so jumping back to it, yes, we are at the swarf machining. So the surface toolpath, when we enable the surface toolpaths, we have all of these other strategies. We have parallel cuts. Now, parallel cuts can be used to create toolpath motion for machining the floor. You can also tilt that tool and be able to cut with the side, as seen in the second image here. And in some of my videos, I have shown just that. If we look at let's see, this part here, I used in a video to show using both swarf machining and parallel cuts to be able to machine with the side of the tool going around these tapered bosses. So with a surface-based path like this, we can also machine walls on parts. As shown in these part files here, and it does a good job. So this particular part file here, if we go back and look at the surface-based options, we have parallel cuts, we have cuts along curve, we have morph between two curves, parallel to multiple curves, project curves, morph between two surfaces, which is very similar to morph between two curves, only instead of the inputs being curves, they're surfaces. We have parallel to surface, which works well for machining blended areas where a boss is sticking up, just like this image shows. And then we have a flow line toolpath. So all of these strategies use common inputs as far as, they share a lot of the same tool axis control parameters and so on. So we'll look at like morph between two curves or parallel cuts. Let's look at the parameters there and kind of see what these parameters look like for our surface-based paths. So we have our drive surface inputs. And then from that we have areas which is going to control kind of the way that the cuts are made. We can define step over values. We have sorting methods for how those passes are going to be handled on the part. We have a tool axis control page. On the tool axis control page, this is where you're controlling your tilting of the tool. How should the tool be run when it's calculating its 5-axis positions? And we can use options like relative to the cutting direction, so we can either tilt the tool forward and back using lead lag, or from side to side using side tilt angles. We can be tilted with an angle where we specify a fixed angle, and then we have options where we can define either a line or an axis that we want that angle to be relative to. We can tilt through angles defined to an axis, or we can rotate the tool around a specific axis. We can tilt through a point where you actually define a point in space, and then the tool from that point is driven down to the surface. You can also have a point below a surface and have the tool run pointed to that point. We can tilt the tool through a curve, and I have several videos showing now the use of curves and how you can use that to constrain the tool angle that's being used. And that's a very powerful tilting strategy to control how that tool is going to go in and actually contact the part. It's very powerful for being able to keep your machine within limits and things like that, and the options that go with tilting through a curve. We can also tilt through lines, where we can create lines along our path that represent the angle that we want the tool to be. And then we have point away and curve away. And those two are very similar to the point and curve options that we saw before, or we mentioned before, only it's the exact opposite, where it's seeing that point below your drive surface, and then the tool is basically contacting through that point that's below the surface. It's always pointing at that point, or the tool is always pointing to the curve instead of away from it. So on this page in general, this is where you're controlling the tilting of the tool. The next page we have is gouge checking. So gouge checking is where we can eliminate or try to correct for problems in the path that gets created. So the gouge check options that we have are, retracting the tool. So if the tool is gouging into a floor or a piece of geometry, we can retract that tool or push that tool down so that it will not violate the part surfaces that we define. We can also tilt the tool. So we can tilt the tool either side to side or front to back using lead lag or left and right tilting strategies. We can also stop the toolpath calculation where there's a collision, and that will just simply end the toolpath at that location. We can also trim and relink a toolpath. So if it finds a spot where the tool just can't resolve, what it'll do is it will simply omit that portion of toolpath and relink to a different spot in the toolpath where it can resume without gouging into the part. So these methods, the one note that I want to say about gouge checking is a lot of times people inadvertently, when they're first learning multi-axis programming, they try to use the gouge checking to solve like major problems with the toolpath, major gouges or major corrections. And the gouge checking, though, is a very powerful tool. You want to make sure that your cut pattern and your tilting strategy is generating a path that only needs minor adjustments. The gouge checking isn't intended to do major corrections, but more like fine-tuning minor errors and minor problems in your path. All right, so let's move on and look at the next page here. Okay, the linking page. So the linking page controls a lot of the aspects of the toolpath as far as how you're going to enter and exit the part. You can apply lead-ins and lead-outs not only to your initial entry and your final exit, but also for the intermediate cuts. So if you're doing depth cuts or you're doing side cuts, you can actually control the individual lead-in and lead-outs for each of those types. And then for when you're actually cutting along the path, you can control how gaps that are along your cut. So if you're making a cut across the surface and in that pass there is a break or something that would cause the system to potentially retract, you can define how you want that handled for small gaps and how you want that handled for large gaps. And then the actual definition of what is a small gap and what is a large gap is controlled with the small gap size, which defaults to 20% of the tool diameter. So based on your tool size, that will determine on what is considered to be a small gap, and then of course anything that's larger than that will be considered a large gap. So that handles the gaps along the cut. But then you have links between slice. So links between slice you can think as these stepovers. So stepovers are if you're machining across the surface, you have each individual stepover and how you want that to be handled, the linking in between those. So you can, again, define small moves or large moves based on a percentage of the tool diameter. You can also define this as a value if you wish and input a direct value. And then links between passes. Now, right now we don't have passes. So if we come in and turn on depth cuts, hopefully we'll be able to see that now we have links between passes. So passes are Z-level depth increments that you're cutting. So if you think like a roughing type strategy, if you're taking multiple passes down in Z or along the tool vector, that's what this section covers. And again, for small moves and large moves, you can control the options based on whether something is a small move or a large. And this one, we just have a simple value that you input. So we don't base this one off of a percentage of a tool diameter. So that gives you an idea of these three different sections. The options that are in here are options like direct, which will simply directly move. You have to be careful using direct because you could potentially violate a part. You can follow surfaces. Follow surfaces is actually going to bring the tool to where that tool is going to check against that surface, and it shouldn't gouge. We have blend spline, so this tries to make a smooth transition with a spline type move. The big problem here is you have to be careful where that spline goes, because it could actually go through your part when it's automatically generating this freeform spline in space. So that's not good for a long distance type move. So, and then we have retract options. So we can tell the system to retract to the feed plane, the rapid plane, the clearance area. We can do incremental from the clearance plane, or we can do a clearance blend spline. So this is a nice option. And what it does is it tries to make sure that it's clearing the part. But again, you have to visually inspect your final tool path very closely to make sure that you're not going to go through the part when using that option. So down at the bottom, so we've talked about these retracts, and we can go to rapid plane and clearance plane, but where are those defined? So those are defined down here in our retracts button. This will open the retracts dialog, and in here is where we set our clearance plane and our different distances for the rapid height and clearance values and things like that. So by default, our clearance area is set to a plane. So we use a flat plane in the Z-axis, and that simply makes that flat plane up in Z. But when you're doing a 5-axis toolpath, you have to think of where is this plane, if it's relative to the Z-axis of the machine setup, is that in the right direction? And then what is this value, this clearance value that we're going to use for that plane? So you might need to change this plane to the X-axis or the Y-axis to have the tool retract in the proper direction. Now we also have the ability to create a cylinder for our clearance area. So if you're working on a round part, this actually works very well because the tool will always retract out to the cylindrical position around the part and then reposition around that cylinder. You get to pick which axis the cylinder is on and what radius value to use for that cylinder. So that works quite well. Another one that I use often is sphere, and it will actually create half of a sphere around your part based off of a home position for that sphere. And then you can define the radial value of the size of that sphere. And this works really well for parts like impellers and you know, small little pieces that you want to create like a clearance bubble is the way that I think about it around the part. So down here at the bottom of this page is where we set things like our rapid distance. So when we're retracting away from a cut or we're going to approach a cut, we have our entry feed distance. So where are we going to change from a rapid motion to begin feed motion, where we're going to feed down to the part. We have an exit feed distance. So this is how far are we going to feed away from the part at a feed rate before we switch over to a rapid move. Next, we have our air move safety distance. So if we're positioning from one side of a part to another, we have this additional safety distance that the system will calculate and make sure that those reposition lines are clear of this value before it starts moving the tool across the part. Okay, so that's the majority of what's on our Retracts page. The lead in and lead outs, which you can turn on and off here on the right hand side. So they are defaulted right now, don't use the lead in or don't use the lead out. You can actually, you know, when you say use lead in, or when you come in here and say, you know, use lead in, lead out. Now there are these little buttons next to these when you enable that. And if you go in there, it brings you to those parameters. However, if you don't bother setting the settings in that dialog, down here at the bottom is the default lead in, lead out. And why we have this in two different places is because you can individually set the type of lead in to be used, lead in or lead out to be used for each one of these options. But if you don't want to set that over and over for all these options, then you can simply come in to the default lead in, lead out, and you can set the lead in on the left, you can set the lead out on the right, and once all those parameters are defined, the system will simply use those if you haven't gone in here and actually define this, because you can see each one of these have a checkbox that says use default lead out, and for you to change the parameters here, you have to turn that off. And so you do have the ability to manually control each of these, or you can just use the default. Okay, so moving on to the next page, we have the roughing page. So in here, we have options like multi-passes. So multi-passes gives us the ability to define multiple passes in. If we're doing a profile cut, we can do multiple passes in with the side of the tool. We also have depth cuts, which allows us to define multiple passes going down by the depth of the tool. So those are two roughing style, like if you're doing, you know, cutting with the side of the tool, or even the bottom of the tool, like if you're machining a floor, but you need to do multiple depth cuts to accomplish the final depth that you need, you can set that up in depth cuts, or if you're working your way in with the side of the tool, you can do multi-passes. We also have other features like you know, creating a plunge style toolpath or a morph pocket type toolpath. We have area roughing, which is specifically used for impellers with splitters and things like that. We can use we can like do transformations on our toolpath. For example, programming a toolpath in a single location that we want to then copy around one of the rotary axes on the machine. For example, programming one fin on an impeller and then translating that to where it cuts all the additional fins. We can do things like mirror the tool path. And then we have sorting options for all those different passes that we're doing if you have those turned on. On the utility page is where we have other kind of unique controls that aren't used as often by everybody. However, they're very powerful features, and there's certain things in here that are extremely beneficial. We have surface radius based feed optimization. So what this is actually used for in 5-axis machining, if you think of a fin and you're wrapping a tool around an edge, that rotary motion as it's wrapping around that edge requires the machine to move quite fast. So you would be able to come in here and define parameters to get it to where it slows that down and it doesn't try to whip that machine around so fast in that area, which could potentially cause bad finish and so on at the machine. We also have tool contact based feed optimization. So if the tool is engaging more material and on the corners of the tool, like when you come into a corner and the contact point quickly is transitioning over to another area of the tool, that can cause chatter. If you think of cutting into a square corner, your engagement goes up. So this feed rate optimization will go in and adjust your feed rate values to try to optimize that cutter engagement. We can define things like feed control zones. So this would be like an area of our part where we want the feed rate to be different than than the rest of the tool path. We can set things for like use rapid feed rate. So we can define where rapid moves that would normally be output as a G0 can be converted over to an actual G1 with a feed rate. So this will eliminate things like dogleg rapids and stuff like that on machines that process rapid motion as a non-interpolated motion. Let's see, we've got feed rate for the different gaps along cuts and links between slices. So the things that we saw on the linking page, we can actually assign different feed rate values to that motion that's found in there. Axial Shift is one that's actually used to allow you to program the tool at a depth. This is used when you're cutting with the side of the tool. So think of like the wireframe tool path or the swarf tool path. You can actually drive that tool deeper beyond the bottom edge of the part and have that applied either instantly and equally across the entire path. You can have it shift over the duration of a tool path. So let's say that we have a tool that has 2 inches of flute and we're cutting through material. The depth that we're cutting is not really all that important because we're trimming maybe 1/8 inch thick material, but I don't want that tool path to always be cutting at that same height on my tool because it's going to wear out that spot. So I would be able to apply gradual for each cut. Then what happens is as the tool is cutting, it'll be dropping that tool deeper, or it'll be lifting that tool up along the cut so that it's using more of that flute area instead of just always cutting on the exact same spot. And then we have some miscellaneous settings down here, max angle step for rotations and set y-axis machine limit, smooth surface normals. These are some specific utilities that will be covered primarily in other videos as we keep moving forward. So that's kind of the utility page has very useful options on it. Not all of these options are used all the time. They're typically more specific things. We've got some great feed rate control options on here that a lot of people don't necessarily know about. But the big ones that's used here for sure are the feed rate changes, and then also that axial shift really works great when you're doing trimming style toolpaths. So that's pretty much all of the surface-based toolpaths have that common set of parameters that you're working from. Swarf machining also has, for example, the utility page. It just has less options. It does have some specific options for like corners, and the multi-cuts is on its own page instead of being in the options page, but we still have the linking page. We still have the gouge check page, although its gouge checks options are limited down to only a few. And then we have like the tool axis control page obviously is simplified based on which options you have defined. And then multi-axis roughing as a toolpath kind of has its own surface paths page where you're defining specifics for the toolpath. The part definition, gouge check again is simplified because it's a very specific setup for this operation. Our linking page is got the same type of options, but again simplified. The roughing page really only has just a couple options, mainly where you're dealing with the stock and things like that. And then the utility page only has just a few of the options as well. So you can see why I was showing the parameters on the surface-based paths, because really the other 5-axis strategies have a lot of the same options. But there's actually fewer of them. So some of those options they're not available for all types. The wireframe toolpath, as we go in here, you can see we've got our tool axis control page, our gouge check page, the linking page, but then roughing has more of these boxes that aren't available, and the utility page has limited options there as well. So looking at all of the tabs from a surface-based toolpath like parallel cuts gives us the most amount of options that we can see in the UI. But they are common across all of them. And as we continue with videos, you'll get a better understanding of how all of these options work on the different pages. But that pretty much wraps up the general overview of the multi-axis features and what the different toolpath types do, and kind of what their options look like for each one. So again, the videos that I plan on making and the videos that I have made, the idea is to give you guys different examples of using these options to successfully program your parts. And so definitely make sure that you're checking out all of the other videos as well. All right, well, that'll wrap up this one. Thank you.